Hello everyone, welcome to another Math Club talk. Today with us we have Aditya Saha, BMath 2019 alumni and MAth 2021 alumni. He was in the University of Florida and he'll be talking about the LS category today. Over to Aditya.
Okay, thanks for organizing everything. It's been a while since I've been back here, and this is the first time I'm this side of the stage. So today's talk is kind of an introduction to tomorrow's talk at the department. So it's supposed to be very introductory. Feel free to stop me at any point and ask questions. You don't even need to raise hands, just ask a question if you have anything. I will try to define everything as much as I can. If I can't, I will explicitly state that. Okay, so what we're going to be talking about today would be something called Lusternik Schnirelmann category. So this is very old, like 1930s kind of stuff. So category theory was not a thing back then. So they just, when Lusternik and Schnirelmann came up with this invariant, they just called it their category. But it's a number, it's a integer, numerical invariant. So today there won't be any category theory, but tomorrow there might, and usually people get confused, but hopefully that's not going to happen. Okay, so the first object that I want to describe is contractibility. Raise your hand if you know what contractibility means, or have you heard about something being contractible, null homotopic, deformable to point. Okay, so I'm just going to define it. Okay, intuitively, if you have a set S inside a space X and some point P, we're going to say S is contractible if there exists a continuous map of let's say S cross the identity to X, the bigger space X, such that let's call it H, such that, so if I'm looking at S down here and you have the interval here, this is the direct product. So I'm saying that there exists a map, we'll call it H, such that in the bottom part it's identity. So any point in the bottom part of the cylinder you have identity, and the top part of the cylinder gets squeezed to a point. So the general idea is that you imagine the second parameter, so I equal to the interval 0 and 1, imagine the second parameter to be time. So basically at time t0 everything is static, and at time 1 all the points slowly come to this. So there exists a deformation of the whole space to a point. Okay? So in topology we usually study objects up to homotopy, so up to deformation. So these are the simplest objects in topology. For example, if you have a torus, for example, a torus is not contractible. One can show it in several ways, but the idea is there exists a little hole here and the inside of the donut is hollow. So you can never continuously deform it to a point. To continuously deform it, you'll have to collapse a hole that will break continuity and so on. Starting from this idea that you can't always contract a space to a point, one natural question is, how many pieces do I need to break a space so the pieces are contractible? Basically, if you don't have contractibility, the next best question is, how many pieces can you extract out of it, each of which will be contractible? So, here comes the definition. Should I use this? Let's use this. So let's say X is a topological space. Then the LS category, it's defined as cat, whatever this notation. Category is N if N is the smallest integer such that X can be covered by an open covering such that each of these UI are contractible. Okay, simple enough. Note that the indexing of the open cover starts from 0 instead of 1. This is due to this is convention, just makes formulas look little bit better in the future. But basically, a corollary of this is, first, what does it mean when cat of X is 0? Getting there? Must be homotopic to a point. So it must be contractible. If the whole space itself is contractible, then you don't need to break it up into pieces. So this follows from the definition that the category of X is 0 if and only if X is contractible. Simple enough. Now, what about category of the spheres? How many pieces do we need to break it into? 2 pieces, right? Because you can have break a sphere into its north and south hemispheres, and each of which are contractible. Each of these are just disks, so you can contract them to the poles. Well, to say cat of spheres is 1, we also need to show that spheres are not contractible. If you know basic topology, you can prove that spheres are not contractible. If you want to talk about, let's say, not homotopy groups, but like homology groups and all, you can show that it's not contractible, but each of these spaces are. The point is, spheres have cat 1. Now, question is, what is category for Euclidean spaces? Yeah, this is the same. It's a trick question. But that leads us to a question: what are the spaces with category n for just any n? One example is, what we'll do is category of the real projective planes or real projective spaces is always n for any n. So for any n, you have a class of examples for which you'll get that. It's not obvious, but one can show, if you know how RPN in general looks, you can easily show cat of RPN is less than equal to n. Why? Because you can, if you remember the structure of RPN, it's like you have a sphere, but you can kind of take away hemispheres and identify the edge boundary with one another. Oh, okay, sorry. So you take a sphere and you have an equivalence on the sphere where you identify any point x with its antibodal point negative x. What you get is RPN. So it's like collection of all points and their antipodal points. Okay. You can think of them as all lines passing through origin in R as well, like Rn as well. Or you can, I don't know, if you like group theory more, you can think of a Z2 action on Sn by reflecting above the origin, like x going to negative x, and the quotient that you get is RPN. There are several constructions of RPN, but basically it's just sphere, but you don't distinguish between antipodal points. Okay. So as you construct RPN, basically what you do is you take off a hemisphere, identify what's left as RPN minus 1. So basically you inductively keep removing hemispheres till you get 2 points, and that way you get a covering with n plus 1 many, because each of these hemispheres are contractible. So you can always cover RPN with a good cover of size n plus 1. Showing the other inequality, this is a little harder. Maybe we'll get to that by the end of this. Okay. Also, we will hopefully today we'll show that category of the n torus is also n. Okay. N torus is just circle, 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 circle. You multiply the circle n times. Okay. Now, in general, computing category is really hard. It's not a simple thing to compute. So what we usually can say are just inequalities. We can give good bounds for upper and lower parts. And one of such bounds is given by dimension. Now, I will try to give a definition for the dimension, but if you don't want to go through the definition, that's completely fine. Just imagine the normal notion of dimension you have. But if you want to be rigorous, here's the definition. We're out of this. Order of an open covering V for V let's say we have an open cover of a space X. Its order is the least integer k such that there exists k plus 1 members of V with non-trivial intersection but not k plus 2. So you can think of order as the maximum intersection number for a cover. Okay? The covering dimension is the least k for which order of for which any open cover has order k. Has refinement lots of words here, but basically what I want you to keep in mind is that in R2, if you want to cover R2 by open sets, you cannot avoid having at least 3 open sets intersect. Basically that's the idea. If you want to cover R2 with like balls or like tiles or whatever you want, if you make those tiles or balls open, there's got to be intersections, and there's got to be at least 3 intersections of degree 3. Okay? Similarly for R1, if you cover it with open sets, you have to have at least like points which are belonging to at least 2 different ones. Okay. So that's the formal definition, but you can just imagine like our usual notion of dimension. Okay. Okay. Okay.
Can't I cover Rn with open sets that are boxes instead of spherical?
Good question. This is an open set, right?
Yes.
So this point in the boundary is not included.
Oh, so it has to open.
So you have to get another box like this. Then the point in this is not included. So now you have to get a 3 intersection. Right? Fair point though. Like if the open part of the open cover is very important. Okay. Now I'm going to state a lemma. I have decided I will do exactly one theorem rigorously. After that I'll start waving my hands. But for the first part I will have to state a lemma. Let U be an open of X of order n with something I'll call a partition of unity subordinate to U or V U. Then I haven't defined what a partition of unity is, and for this talk it doesn't matter. It's just something that is always present for smooth manifolds and nice enough spaces. But when this happens, then you can rearrange the open covering in a nice way. What do I mean by that? Then there exists an open cover G, let's index it with beta, open cover refining such that actually the indexing will be twofold. So I'll have two indices, I, beta, where I goes from 0 to n. Open cover refining U such that G I beta intersection with G I beta prime is empty. What do I mean by that? If you think about these two indices I and beta as independent indices, what I'm saying is that given an open cover, which can look horrible, it can be uncountable, we don't care, you can split it into n plus 1 different categories, each of which are pairwise disjoint open sets. So G1 beta and G1 beta prime will not intersect. G2 beta and G2 beta prime will not intersect. So if you think of like U, let's say we are, we have to use okay. In this case, we have a weird open cover, but think of the eyes as colors. So here I can paint it in two colors. The first color would be, or maybe three colors actually. The first color would be these balls. The second color would be these balls. And the third color will be the empty, the ones that I didn't put any marks on. What I'm saying is that now the elements of the shaded balls are mutually disjoint. The elements of the dots are mutually disjoint, and the elements of unshaded parts are also mutually disjoint. So what we have done here is, given any cover, we have separated it into like 3 subcovers. Each of them are just like disjoint colorings. Okay, this is very important. So as soon as you get a partition of unity which is subordinate to an open cover, you can break the cover up into nice enough spaces. And the proof in typical topology, yes. Which one? N? The order of the. No. We'll use the dimension in coming up, but yeah, as long as you have a partition of unity for a cover with order n, this is fine. Naturally, you want to minimize the number of colors, right? Saying you can just color it with infinite colors, you don't really get anything. Obviously, each of them will be disjoint. But what you want is to have the least amount of colors possible. That is where the minimal order and the dimension comes in later. Okay. What is the proof for this? It's left as an exercise. Primarily because I don't want to define partition of unity, but once you define partition of unity, you can sit with it for like 20 minutes. I'm sure you'll figure it out.
In the definition, what is
Yes.
a refinement of order K?
Oh, I did not define that, did I? So let's say you have a open cover and another open cover U prime. Okay, it's a simple definition. So we say U is a refinement of U prime if for all elements U belong to U, there exists an element U prime belonging to U prime such that U is a subset of U prime. So these are all collections of open sets, right? So all open sets here are contained in some open set here. So the typical picture for this is that if I have a cover of this square with 4 sets, this finer cover is a refinement, because every element on this cover is contained in a bigger box. Okay. Any questions so far? Okay. So now we have this random set theoretic, not set theoretic, point set topology, and then this random homotopy theoretic definition. What do we get from there? There you go.
By this definition, wouldn't the dimension of the natural numbers be 0?
Yeah. That because natural numbers are points. As a topology, it has the discrete topology, right? But that's a very good point. If you come to my talk tomorrow, you will see there is a notion of asymptotic dimension under which natural numbers will have dimension 1, because they kind of look like lines. Sorry about the advertisement. Now we come to the first non-trivial theorem of today. For a space X, we have the inequality, the LS category is always less than equal to the dimension. Now, this looks too nice to be true, so it's not quite true. We need some adjectives over here. What adjectives? For path connected, that's natural. If you don't have path connectedness, you can just increase category arbitrarily. We need a little non-trivial adjective, locally connected. Locally contractible, actually. Locally contractible, and even more, we need paracompact. For path connected, locally contractible, paracompact space X, we have this inequality. Now, naturally, what do they mean? I'm not going to define each of them. But locally contractible is what it states. Basically, around any point in the space, there exists a neighborhood which can be contracted to that point. Okay. So like normal looking spaces, like not Z, but R, for example, or any manifold, if you know about manifolds, because locally manifolds are Euclidean spaces which are contractible. Paracompact means, I'm just going to say the definition. For any open cover, there exists a locally finite subcover. That's it. For compact spaces, for any open cover, there exists a finite subcover. That's the definition for compact. Para just means instead of finite, you mean locally finite. So, given any covering, open covering, you have a locally finite subcover. So any point will be contained in at most finitely many elements of the cover. Don't think about these adjectives too much, because most of the nice spaces we study in day-to-day life have this. I could have stated this for manifolds itself and everything would have been nice. So, proof. The proof is actually easy. Suppose, assume dimension X equal to n. Given that, find an open cover of order n, because follows from the definition of dimension, you can have a open cover of order n. Now, this paracompact locally contractibleness implies that there exists a partition of unity. I'm not going to explain this. Now, from the lemma, you can convince yourself that there exists an open cover G equal to which is good. Basically, those colors that we have constructed using the lemma gives us our contractibility. Why? One can show that each of these colors are contractible because of local contractibility. You can contract each of these colors to their individual points, and by path connectedness, you can contract those points to a single point. Hence proved. If this doesn't make sense to you and you want to argue about it, feel free to do so after the talk. Questions? Yes?
What's the dimension of x given those conditions always have to be finite?
Yes, because paracompact. Imagine infinite dimensional spaces. If you have encountered like function spaces and all, like if you have an infinite dimensional space, you can always get basically too many neighborhoods. So paracompactness fails usually. So paracompactness usually implies it's finite dimensional. Okay. I mean, also, if this is infinite, trivially, this statement is true. So either cat can be finite or infinite. So if it's finite, finite is less than infinite, we're good. If it's infinite, infinite is equal to infinite. I'm not going to say more about that, but I'm going to say this doesn't make a lot of sense if things are infinite. Yes? Yeah, that's the whole point. Yeah, so basically what you start with is around every point, because of local contractibility, there exists a neighborhood which is contractible to the point. Using the dimension, find an open, like whatever, refinement of that which has order n. Now each of these patches, you're right, because each of these, the whole color shades is not necessarily contractible, but because of our choice of our individual patches, we know that these individual patches are contractible to points inside the patch. That's true. Yeah. So you can contract each of them to these bunch of points. But for a path connected space, any discrete set of points, you can join it with path and homotope it into a single point.
So now we are looking at it in the bigger space.
Yes. Yeah. By itself, obviously, it's not going to be contractible. That's why I think, I never mentioned a space as a contractible space. I always like looking at contractibility as a subspace. Okay? This is, okay. We always have an ambient space for us. So that gives us our first non-trivial result. The dimension is always an upper bound. So in each of these cases, the projective plane, projective space is always n-dimensional, because locally the projective space looks like a Euclidean space basically. Similarly, the torus is product of n one-dimensional spaces, so the dimension is always at most n. So the category is less than or equal to n. Now showing the category is equal to n will come after this. Okay? Any more questions? We're gonna take a detour. No. Ah, there you go. Raise your hand if you have heard about cohomology. You don't need to know what it is. Have you heard of the word cohomology? Keep raising your hand if you know what it is. Okay. Where's the eraser? Oh. I'm gonna start with here because this is the least important. The main problem in calculating this category is usually the lower bound, because you can always kind of come up with a partition of a space, but to show that the partition is optimal is a very hard problem. So we need some lower bounds, and algebra helps with that. So relation cup product. Now, I'm not gonna try to actually define cohomology and cup products from the start. That's gonna be a while. What I'm gonna do is wave my hands. Let's say X is a topological space and R be any commutative ring. So it's fine if you don't know what that is. Imagine R is just integers, Z. Then by some black magic one can construct these groups which we'll call our cohomology groups with coefficients in R. And this is not just a group, this is a ring. It's a graded ring, in fact. So there exists H0, H1, H2, and so on, goes till infinity, where there exists products which are graded. So you can just imagine these are just groups, but there exists a product. So alpha so let's say an alpha and beta in H1 goes to H2. So alpha cup product with beta belongs to H2 if alpha and beta belongs to H1. You can also imagine these as like polynomial rings. So these are all the constants in a polynomial ring. These are all the monomials in the polynomial ring. These are all the binomials in the polynomial ring. And the multiplication is the usual multiplication. So a monomial and a monomial, you multiply, you get a, not monomial and binomial, it's like 0 degree polynomials, 1 degree polynomials, 2 degree. So these are linear, these are quadratics, and so on. So you multiply two linears, you get a quadratic, and so on and so forth. Okay? It's not important to actually know the definition of this, but point is it's an algebraic object that you can construct. Now, by this black magic, we have constructed this graded algebra, a graded ring actually. So, you can define the cup product, cup length is the smallest k such that alpha 1 cup, alpha 2 cup, so on, cup alpha k is not 0 or in H0. This is a super, like there's so much abuse of notation here, I don't even know, but like essentially there exist k elements, might not be distinct, there exist k elements in this collection of groups which give you a non-zero product. Most of these products end up being 0 after a while, so this is a genuine invariant. So you just measure how long can you go for, okay? That leads us to our second theorem. This is one of the most general theorems I've ever seen in topology, like period. For any x belonging to top, so any topological space and any commutative ring, we have the inequality cup product of x is less than equal to category of x.
Could you explain what the top product is again?
I did not. That's your answer. There exists a product structure on this. So because for different groups it's different. So it's I'm telling you, the cohomology is just a sequence of groups on which there exists a product structure. For a given space you can construct it, of course, but
And you denoted the product by?
yes, it's like the cup. Okay, this product is called a cup product because it looks like one. Okay, yeah, you can treat these as axioms. That's actually like a legit way of learning cohomology. One can define cohomology just using axioms, and using some theory one can say that they exist. So like it's completely an existential statement. Okay, so it exists, trust me bro. So proof of this, I don't think I should present a proof because I haven't defined like 80% of the things in the definition. So, but if you're interested, it's a very beautiful and cute proof, like 4 lines, but it uses some machinery. It's one of the most beautiful proofs ever. So, if you have the time, talk to me. It's to be done later. Okay.
Over here, alpha 1, alpha 2, up to alpha k belong to which of the groups?
Could be anything.
Could be anything.
Yes. So each alpha I belongs to the whole collection. Okay. If you take the union of everything, we call it H star. They can be anything. Okay.
So is it sort of like taking the tensor algebra by taking the great sum of all the vectors?
Not quite, because in tensor for a tensor you can get things like alpha tensor beta, and the cup product can be defined in terms of the tensor. So in which sense it is true, but it's not quite the tensor algebra. Okay, it's derived from one. Okay, there definitely exists a lot of relations which kill most things. Okay, like for most cases this product structure is very trivial. Okay, yeah. You can say it's like a very huge quotient of the tensor algebra. Okay, so the point of this theorem was not to prove it, but to use it. Again, which is hard because I haven't defined anything, but even without the definition, we know some statements which are true. For example, not again. How am I doing on time? How long has it been? 45 minutes? Okay, cool. Just some examples, then I want to just do the last thing. So, it is known that the cohomology ring for torus, if you take the coefficients in rational numbers, it's the exterior algebra, like n-fold exterior algebra. Okay. Don't have to know the definitions, whatever, doesn't matter. This is not a lecture. Point is, this is generated by n elements, each of which are in this exterior algebra. The multiplication behaves in some ways, we don't care. Point is, it's generated by n elements, and the maximum cup product or maximum product here is also of length n. So, we know that cup of Q of what? The n torus is equal to n. Yes. Oh. You're right. Of course, yeah. Smallest k would be 0, but smallest k would be like 1. Anyways, so cup product for this is just a very algebraic calculation given any cell complex. You can do some algebra, you can feed it to a computer, you can do whatever, and that will spit out a number. But point is that number gives you a lower bound for this geometric invariant. So this gives us LS category of the n torus is always n. We earlier remember, yes. It's called the exterior algebra, like this one. Yeah, it's called the exterior algebra. It's like, I mean, I can define to you, but it's not gonna make sense. But it's basically some kind of n many copies of Q. You take the tensor product, and you quotient it out with some certain equivalences. So these various different kinds of algebras arise as various different like relations between products. Basically, different kinds of products. There's exterior algebra. There's yeah.
Is it like a cross product?
A cross product becomes abelian, right? Like this is the direct product. This not necessarily. Like, actually, this one is it's not a cross product because the dimensions don't match. It's like it's n dimensional. A cross product. I can explain to you. It's not the cross product. Okay, I will explain to you. Okay, it's not commutative, is what I'm gonna say. Like. It's actually equal. Yeah, a wedge product is an example of this. Yeah, if you have like differential forms or something, it's the same. Okay, another example is these cohomology groups are very well understood basically. So if you have the complex projective space, which is just RPN, but instead of working with the real numbers, you just work with complex numbers, you have similar equivalences. We can say that they are also equivalent to this algebra of polynomials where you quotient out by the n+1th power. One can see that this implies cup lengths over Q over CPN is also n. But here we're not so lucky, because what's the dimension of CPN? Any guesses? Huh? 2n, exactly, because C has dimension 2. So we know that the category of CPN, we haven't written it here, so let's say here, n from there is a lower bound for category of CPN is upper bounded by 2n. There exists more fancier methods to compute the exact number, but it's between n and 2n. But our H star of RPN over Q is isomorphic to the same ring actually. I'll call it T. Cup Q RPN. They're not, I said they're isomorphic, but like they're not isomorphic as graded algebras, because this W has a degree 2, this T has a degree 1, but we don't need to worry about that. But point is, cup length is n. Because of that, we have this inequality as well. N is less than or equal to cat RPN, which is less than or equal to n itself. So RPN has also category n.
Why are we working over rational numbers here?
Because we are given a freedom of choosing any R.
Oh, okay, so we could have worked with.
Yeah, but we wouldn't have nice formulas. Rational numbers have a very nice property that torsion, I don't know if you know about torsion, but it's like things of finite order, things work very well in rational numbers because rational numbers are field.
But the answer would be the same regardless.
Yeah, but it'll give you a different lower bound. We need a lower bound.
Okay, fine.
But the answer will be different and that might not give us the cup product nicely. Okay, so without the rational coefficients, these look slightly different. Okay, that's why this is so powerful, because on the left hand side you can choose any ring that you want, and on the right hand side it's independent of the ring. It's a property of the space itself. So for a given space you have usually a choice of rings, and people usually take Z mod 2 or Q or some other fields usually. Okay, more questions? Okay, now let's switch gears a little bit. We're going to talk about geometry. Why is this a thing? Like what's the motivation behind defining such a random object? In 1934, when Lusternik and Schnirelmann were doing their work and came up with this, what they were actually studying is what's called the critical points of smooth functions. So that was, and there still is, a very big topic. Nowadays people use Morse theory for that, but Morse theory wasn't around at the time. So I'm going to try to give some motivation behind how this was constructed. Okay. Now, I'm going to assume we all know what a manifold means. If we don't know what a manifold means, a manifold is a topological space which locally looks like a plane or a space. Think of surfaces. So, it's like a locally homogeneous topological space. You zoom in at any point, it will look like a plane. This is not the good one. Okay. Let f from a manifold to the real numbers be a smooth function. Okay. Any point P is a critical point if the derivative at the point P is 0. So, the derivative df evaluated at the point P is a map from the tangent space at P to the tangent space of R, which is just R. So, this is a copy of Rn. So, let's say M is a manifold of dimension n. So, this derivative is a linear map from Rn to R, and I'm saying that for P to be a critical point, this map needs to be 0. Okay. It's the same as you do in real analysis, and the critical point is non-degenerate, or actually the critical point is degenerate. So, P is degenerate if, what do we know in real analysis? It's a degenerate critical point if the second derivatives are 0, or second derivatives are 0, yeah. But for us, the second derivative will be a map between Rn to Rn. So, the second derivative, the Hessian of the function evaluated at P, will be this matrix with respect to a local chart. You can think of it as dxi xj for I and j. This matrix is non-singular. So, these are the bad critical points, so as to speak, like where the function is like really stationary at the point and it's not well behaved. So, the basic question at the time, yes, go ahead. Did I miss degenerate? Non-singular means, oh yeah, of course. Yeah, I want the determinant to be 0 if it's degenerate, so yeah. Good point. So, question is, knowing a smooth function what can we say about our initial manifold M? So, if you have done any kind of like linear algebra, operator theory, functional analysis, there's this notion of dualization, right? So, you have a vector space, but then you want to look at all functionals on a vector space. So, you look at all the functions from the vector space to R or to C or to whatever field you're working with, and you ask, given a function, can we reconstruct the initial vector? So, they were asking the same question but for smooth manifolds. So, you're given a smooth function on the manifold, can we recover information about the manifold itself? And the spoiler to this is a lot, but only when the critical points are non-degenerate. So they were working in like 1934, 1935. In 1960s, a guy called Marston Morse, he actually proved that when a function's critical points are all non-degenerate, then the homotopy type of M can be recovered. And even you can recover a cell structure on M just from giving a smooth map. So that was one of the biggest discoveries of that time. And since then, all functions whose critical points are all non-degenerate have been called Morse functions. Yes?
From one smooth map.
One smooth map. You give one smooth map, not all. I mean, if you are given all continuous maps from a space to another space, you know the, yeah. But this is much, much, much stronger. It's like one, right? That's like vector spaces. Like if you have given a functional, you have a map from vector space to R, you can say a lot of things about vector space, right? So, but we haven't arrived in 1960s yet, so we are still in 1935s. So, what can we say? Still a lot actually. I'm gonna try to.
What is TPM?
Which one? TPM. It's like it's the tangent space.
Tangent space.
Yes. A derivative is a map from the tangent space to the tangent space usually.
So is the tangent part of the start? That's why you're taking.
Yeah. I'm going to give a baby version of Lusternik and Schnirelmann's theorem. This is Lusternik this is baby version. We're assuming a lot here, okay? So, where is it? Yeah. Let's say M is a compact smooth manifold. Then, the number of critical points, note that I didn't put any function on it, is greater than equal to the LS category of M plus 1. Why didn't I put a specific function on it? Because this definition is independent of it. So, crit of M is the infimum of number of critical points of function from M to R of smooth functions. Sorry for the sloppy handwriting, but you look at the infimum of all possible number of critical points. Yes. Smooth manifolds. So can I give a definition? Probably not. I would imagine a torus, like a manifold which is smooth. Like a manifold I haven't defined, smooth I haven't defined. But imagine structures which are like a tetrahedron. No, because it's not smooth at the corners and at the edges. But a sphere, smooth. These two are homotopy equivalent because you can deform one into the other and back. That's fine. But I'm specifically talking about smooth functions, smooth manifolds, only because I want to study smooth maps on them. Like there's no easy way to define a smooth map if you have degeneracy at the corners and all, right? So I'm just going to think about shapes like this locally, which look the same everywhere. Okay. Or like, yeah, the torus. These are all two-dimensional examples, but imagine in higher dimensions also you have similar things. Okay.
Like where every point has a nice tangent space which can move around nicely.
Yes, that's one way of looking at it. Around every point, very nice. You have a tangent space, and you can smoothly deform the tangent space as well. For example, here, if you trying to move this tangent space into another face, you don't know what to do at the edge. You can go till the edge, but then you don't know what to do. There's infinitely many possibilities to orient the tangent space. So, this is the thing that I want you to remember.
Why do we need to take infimum? Can't we take minimum?
It's the same. Yeah. These are all discrete sets, infimum, minimum, I don't care. Like these are all integers, so it should be okay. Was there any other question? Yes. Yes. Very good question. We'll get to that. Yeah, and the point is this is the infimum over all smooth functions, as you asked. So this is even more surprising. The infimum is lower bounded by the LS category. Note that this is a very smooth property of a manifold. This depends on what metric you are putting on it, what are the diffeomorphism and so on. The right hand side is a homotopy property. So even if you modify the space, so you can define the right hand side for this guy, but you can't define the left hand side for this guy. So this is a completely topological property, and this is more of a differential property, differential geometric property. That's what makes this theorem so powerful. And I have just restricted myself to compact smooth manifolds, but this can be stated for non-compact smooth manifolds as well. This can be stated for compact C2 manifolds. So you can remove compactness as well. You can remove smoothness as well. You just need it to be twice differentiable, and the derivatives need to be continuous and so forth. You can even remove the manifold part of it, but you can think, I don't think people here are interested, but there is a thing called infinite dimensional manifolds. So they're called Banach manifolds and so on, where the tangent spaces are no longer finite dimensional vector spaces, but they are Banach spaces, arbitrary. One can define, this theorem holds in that situation as well. They used this to study what is called the calculus of variations, at which point you need those function spaces, those infinite dimensional things. So this is a very, very, very general theorem. We're just looking at the baby version of it. Okay. And in the 60s, when Morse came around, how much time do I have, by the way? Oh no. How much time can I take? Should I stop? Okay. This is more of a kind of a philosophical ending to the talk. I will try to not do much math anymore. Now I'll try to present what is later known as Morse theory. So in the 60s, this question became very important. I don't know much of the history, so I don't know. But in the 60s, Morse proved that the cellular structure of a manifold M can be recovered from one smooth Morse map. And as a corollary of that, I'm not going to say exactly how because I am omitting some details here. He showed that the critical number, but now not over all smooth functions, but all Morse functions. So just to remind you, Morse functions are all smooth functions whose critical points are non-degenerate. So the good ones. The infimum of critical number of critical points of all Morse smooth functions has a lower bound given by this quantity. This bi of m, they are called Betti numbers. If you have encountered topology at some point, the Betti numbers are basically dimensions of these vector spaces. Okay. So it's also an algebraic invariant. Okay. But the interesting thing is, this is an integer is always greater than or equal to the lower bound which we found earlier. So in the 60s, we got a much better lower bound, but it's only for Morse functions. Now the interesting thing is the space of all Morse functions from M to R obviously sits inside all the smooth functions. So we call it C infinity, let's say. This is obviously a smaller subset of over what we were optimizing, but he showed that is dense. So although in theory we are going into a subset of functions, but this subset is dense in it. So they're arbitrarily close to any smooth functions. You can approximate any smooth function with these Morse functions. So essentially, this inequality is true even for normal smooth functions. Essentially, it's not true for all. I'll give you an example. But and partly because of that result, people this is a good and bad thing. People became so excited about this Morse theory, which is in itself very nice, that people kind of forgot about the LS category, and the whole topic of LS category was like dormant for like 40 years after that. Only recently they have started again. But closing remarks, I'm gonna draw a picture. Huh? Betti numbers, yes. Imagine a torus, like this nice donut. Let's say I have embedded the torus into R3, and let's say that is the z-axis. And imagine a function from the torus to real numbers which just measures its height. Okay. Any such embedding of the torus will give you a function, M to R, right? So, intuitively, can anybody guess how many critical points this has? This is the z-axis. 2, I have 2, I have 4. The correct answer is 4. we have one critical point over here when the function has a local minima. We have one critical point over here where the function has a saddle point. We have one critical point over here when the function has another saddle point. And the last critical point where it has a local maxima.
What do you mean by the function gives the height?
What does a function mean? It takes any point in the torus and assigns a real number to it.
So it basically extracts the z coordinate.
Yes. Yeah. So that function is for this particular embedding. So if you move the torus around, of course, the function will change. The given function. So, what are the Betti numbers for torus? Does anybody remember? Okay, I'll just write down. It's like 1, 2, 1. Okay? In dimension 0 we have 1, in dimension 1 we have 2, in dimension 2 we have 1. So, if you look at this, it should appear a little suspicious. So, where this quantity is 4, this is 1. So, this gives us cat of T2 is less than equal to 3, which is fine, but we have already proved that cat of T2 is 2. So this is not a good bound. But here's why Morse function versus smooth functions are important. Imagine you can have several different embeddings of the torus, each of which giving a different functional. Now imagine the little hole in the donut and you're shrinking it, okay? And you shrink it to a point. So you have this degenerate embedding of the torus into R3. Now, since we haven't crossed inside, we're still touching, it still gives us a smooth function. It's not, so how many critical points do we have now? We have 1 and 2 on the top and bottom, but the inside saddle points have, degenerated into one critical point. So, there's only 3 critical points. Now we are good. So number of critical points for this function is 3. So cat of T2 is less than equal to 3 minus 1 equal to 2. So since we are getting outside this constraint subset, we can actually arrive at the precise bound just by critical numbers. So this is okay, I think this is a good place to stop, and thank you for being so patient. You have questions?
Does anyone have any questions?
In the last part,
Yes.
how is the middle thing still a critical point?
Say that again?
Yeah, why is the middle thing a critical point?
Because if you look at the neighborhood, it will, like, it's not strictly increasing in the neighborhood. So you're still looking at the height function.
Yeah, but the derivative has to be 0, right?
You can show it. Like, I can actually give you an explicit, like, the function statement.
Okay.
like this corresponds to a function. I can give you the exact statement of the function, and you can check that.
Can you like geometrically show it that the slope is becoming 0 or something?
Yes, because the slope here and here is still 0.
Even when you're compressing.
Yeah.
Oh, okay, fine.
Right. I'm just compressing it from all sides. If you're reducing the size of a circle, the angle doesn't change, right?
Yeah.
I'm not compressing it like squish this. I'm compressing it like straight to a point. So it preserves all the angles, and it's still 0, 0, 0, 0, 0, 0.
Any other questions? Okay, I have one question.
No, there's
okay.
this one.
Yeah.
Yes. Yes. Tomorrow's colloquium, I will be talking about this LS category, but in the large scale setting. So, looking at note that everything we talked about was for like compact manifolds. If you remove compactness, you look at like really large things and how things behave at the end, like at the boundaries of them, basically. We have similar inequalities there, which, yes.
Any other questions?
Yes.
Calculating the cup CPN, could we have chosen a different ring to give us a better bound for the category?
I think that's what they do eventually, but not. I don't remember the exact formula for let's say R. Like if we replace it by R, we have to see what kind of torsion you have, because this eliminates all the torsion. So there is a priori some torsion part to this, and I don't think just by these techniques you can improve the lower bound very easily. I'm pretty sure you need some more subtle machinery for that. Yes. But I'm sure there are other fields for which it's exactly that, and so Q is not the unique one. Yes.
So my question is, how is this an embedding? Because you are sort of identifying the inner circle to a to a point. So shouldn't there be a problem?
Yeah, like it's not an embedding in the sense, because you define embedding as a map where you have all the differentials to be non-singular.
Yeah.
Right. So this is not an embedding.
I see.
It's just a copy of it. It's degenerate, obviously. That's the degeneracy
I see.
that creates that. Yeah.
Okay. So any other question?
Yes. Which one are we talking about? Oh, okay. No. Yeah, definitely. Like this, you're talking about this, right? Cup R, this cat X, right? Yeah. This you can't always find a ring. Definitely. Like there are examples where this thing is infinite, but this thing will always be finite. And these are like very I don't want to say elementary, but like simple approximations. Approximating cat is like a very hard problem in general. Like, it's tied to many open problems in group theory. Yeah.
Any other questions? If not, we can thank the speaker once again.
Thank you.